Good morning. Welcome to class. It's Wednesday, April 29th. So getting pretty close to the end of April. So tomorrow's the last day in April. Uh, Also my wife's birthday. So yeah, and then getting into May. So really soon, May 14th is AP test. And then the year is over the week after that. So we're getting really close to the end of everything. Just try to keep up with your work. If you're behind, just try to catch up, follow through the videos. If you need help catching up, feel free to reach out to me either on Google Classroom or through email or pretty much anything like that. And I can help you catch up. Um, College Board put out a video. I attached it to this assignment. I also put it on a separate assignment at the top of the classwork section, and it talks about what the AP test will look like, and they'll kind of go through it. So make sure you watch that. It sounds like they want you to either write out your answer or type your answer into some sort of Word document. And then when you go to turn in your answer, it'll give you 30 minutes for the first one. And then after 25 minutes, it'll show up as red, and that's saying, hey, you need to get your test turned in now. And you can either upload your Word document, you could upload a picture, or you could copy and paste into a text box. And they go through exactly what to do, how to title each page. You have to like write your ID number and things like that. So go through and watch that. The other really big thing is you're getting your test ID through email. So I really need to know if you're not getting College Board emails for any reason. If you never got the College Board email talking about how the test is going to work, you need to talk to me because we need to change your email address so you will get the link. It sounds like they might post a link on College Board as well, but the video didn't say that, so I'm not sure if that's how it's going to work. So yeah, you might be able to get in through College Board, but you really need to have your email address linked to the email you actually read. So make sure you contact me if you never got that email. If you haven't looked at your emails, please be looking through your emails. That's going to be really important coming up. Other than that, yeah, let's just begin. Sorry I posted these two kind of late. I forgot to actually put these up, so I put them up tomorrow afternoon. So if you haven't tried these again, go through, try to do them first before we work through them. All right, so here we are. So here we have a spacecraft of mass m in a clockwise circular orbit of radius r around the Earth. As shown in the figure above, the mass of the Earth is me. And notice how convenient they put the radius to the center of the Earth, right? Anytime we're dealing with force of gravity over a long distance, we're going from the center to center. So center of the Earth to the center of the spacecraft. So that radius is looking good. So A wants us to, in the figure below, draw and label the forces, not components, that act on the spacecraft. Each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. So what forces do we have acting on the spacecraft? Force of gravity. What else? Only force of gravity. And force of gravity is pulling in directly towards the center of the Earth. Yeah, that's the only force we have, pointing directly to the center of the Earth. So again, there's nothing pushing it sideways. Initially, you had to fire a rocket. Initially, you had some push that made this thing go sideways. But once it's in that circular orbit, there's no sideways force. So if we're in a circular orbit, all we have is a force of gravity pulling us towards the center of the rocket. Not the rocket, to the center of the Earth. Right? And that's only, I guess that's 2 points. So we see here, for an arrow directed towards the center of the Earth. So 1 point if you drew the arrow towards the center of the Earth. And then for a correct label on the arrow representing gravitational force, where the arrow is pointing towards the Earth center. So you have it pointed towards the center of the Earth, and you labeled it as the force of gravity. And again, when you write this out, you have to do force of gravity. You can't write just lowercase g. If you just wrote lowercase g, that's wrong. That's implying acceleration due to gravity. So FG. And that was up to 2 points. If you capitalize the G, yeah, that should be fine. That's how I normally write it. F lowercase, like a capital G for the subscript, just to signify it's Newton's law of gravity. But yeah, that should be understood. I was like, where's the question? I forgot to go back to the thing away from the key. All right. Now we have this. I don't think they're going to ask you a derivation question like this, but it's still good to go through. They could still ask you how something would affect another thing, and writing out the equations would be important. But B1 wants us to derive an equation for the orbital period t of the spacecraft in terms of mass of the satellite, mass of the Earth, radius, so the distance between the center of the Earth and the satellite, and any physical constant, so like gravitational constant as appropriate. If you need to draw anything other than what you have shown in part A to assist your solution, use the space below. Do not add anything to the figure in part A. So that's kind of an important thing. If they ask you to solve something here in one part, don't go back and start writing all over the previous part. That will change your answer to the previous part, and you can start losing points if you do that. All right, so how are we going to start this? So how are we going to start this to get period, orbital period, the amount of time to complete one orbit? Orbital velocity. All right, so we can start there. So the orbital speed, we can do distance over time, and time for one orbit. So this is the distance for one orbit. How far does this go in one orbit? It goes in a complete circle around the Earth. So this is going to be the circumference of the orbit divided by the orbital period, or 2 pi r divided by the orbital period. All right, so I know 2 pi, that's just a number. I know radius r, but I don't know the orbital speed. So I need to get the orbital speed using some other equation now. Multiply. So speed times orbital period is 2 pi times radius. Centripetal acceleration, there we go. So I know my centripetal force is caused by the gravitational force. Now, there's College Board webinars for the AP teachers, and the people who make the test are on there. And one of the things that they randomly just harped a lot on was that centripetal force is not an actual force. Centripetal force is always caused by other forces. So here, centripetal force is caused by the force of gravity. So that makes it really sound like that might be on the test this year. I mean, they might have just been using it as an example, but it's suspiciously, they said a lot about this. So centripetal force is not a force we draw in a free body diagram. It's a force caused by the forces on the free body diagram, the net force making this thing turn. All right, so centripetal force is mass times centripetal acceleration. That force of gravity, we're at a large distance from the Earth, so I can't just use mg, where g is 9.8 meters per second squared. As we get higher and higher above the Earth, our acceleration due to gravity decreases. So we have to use our Newton's law of gravity, gravitational constant, times mass of the satellite, times mass of the Earth, divided by the distance between the center of the Earth and the satellite squared. Pretty quickly, we can divide out the mass of the satellite. Again, the mass of the satellite does not affect the rate that that satellite orbits the Earth, which is really good. The people inside the International Space Station orbit at the same speed as the space station itself, so people aren't getting slammed into walls really hard. That's good. They just float together along through that orbit. Centripetal acceleration is speed squared divided by radius. So gravitational constant, mass of the Earth divided by radius squared. And this is a capital R. I can multiply radius over. So if I multiply radius over, so speed squared, gravitational constant, mass of the Earth times radius of the orbit divided by radius of the orbit squared, R divided by R squared, gravitational constant times mass of the Earth divided by radius of that orbit. All right. So this is speed squared. Let's just do that. So this is speed squared. So this is not squared. So let's just square this whole equation right here. So let's do VT squared 2 pi r squared, just to kind of be a little bit lazy. So I have speed squared, speed of the orbit squared times the period of the orbit squared equals 4 pi squared times the radius of the orbit squared. So now I know speed squared is equal to this. So instead of speed squared, I can write this gravitational constant, mass of the Earth divided by radius of the Earth, times the period squared is equal to 4 pi squared times the radius of the orbit squared. I can multiply radius over, so I get radius cubed, 4 pi squared radius cubed, and I multiply radius over. But I need to divide, why did I do pi? This should be a 4 pi squared. And then I can divide gravitational constant and mass of the Earth. And this is period squared. And so to get the orbital period, we would take the square root of all that. 4 pi squared radius of the orbit cubed divided by gravitational constant divided by mass of the Earth. And we can pull some of those things out of the square root. I can pull the 4 and the pi squared out of the square root, but that doesn't make it look too much nicer than what we had. All right, so let's look at this. All right, so 3 points. One of them is for using or implying Newton's second law and equating centripetal force to gravitational force. So as long as you got that the gravitational force equals the centripetal force, I don't think you have to go all the way over here. I would say that just using force of gravity is equal to mass times centripetal acceleration should get you that point. We get a point for determining the speed of the spacecraft is going to be the circumference of the orbit divided by the orbital period. And then we get a point for a correct answer that's algebraically equivalent to this, which means we don't actually have to get this far. So this is where they're saying it's acceptable to leave in terms of period squared. I would also argue that that point was earned the second we combine these two equations. The second I combine this equation with this equation into one, I would say this gets me those full points because this is a mathematically equivalent expression. So if you got to the point where you got your speed is the circumference divided by period of the orbit, and you got the speed using your setting your centripetal force equal to weight, and you combine those two equations into one, I would say you get that point. As long as you could reduce your equation into this form, you get that third point. Although it is equivalent to the correct answer, but not simplified. Let me see. So that would be... Yes, you get that point. That is a mathematically equivalent answer. Yeah, because you divide, it's divided by square root divided by square root of r. So you get r to the 3/2, which this is r to the 3/2 when you do that. Yeah, that's a mathematically equivalent answer. I would give you, as long as you did the other two things along the way, that would be all 3 points. So yeah, if you're wondering the answer, I'm looking at it. She wrote it like 2 pi r divided by the square root g me divided by r. And that is correct, because when you divide by the square root of r, it's the same as multiplying by the square root of r. So we get 2 pi r times r to the 1/2 divided by square root of g me. R times r to the 1/2 is equal to r to the 3/2. 2 pi r to the 3/2 divided by square root gravitational constant, mass of the Earth, which that also works because I can pull out the 4 pi squared, that becomes 2 pi. R cubed square rooted is r to the 3 divided by 2 for the square root, and then we have divided by the square root of gme. So you still get that point. All right, so B2. 2 is more like the type of thing I expect them to ask on this year's AP test, more so than a whole lot of math. But I could see them asking you an answer where it would be good to go through and do the math in order to prove yourself, if that makes sense. So here we have a second spacecraft of mass 2m placed in a circular orbit with the same radius r. Is the orbital period of the spacecraft greater than, less than, or equal to the orbital period of the first spacecraft? And notice the reason I didn't have to write any words in B1 is it said derive. So because it said derive, I didn't need to do words. But here it's saying to explain my reasoning. So for 2, I can't just write math. It says explain, so I can write math, but I need to also have words to tie my answer together. So I put the second spacecraft different mass in the same orbit. Is the orbital period greater than, less than, or equal to the original? Yeah, equal to. So here we see all the way back here that our mass divided out of our equation, right? So the mass of the satellite has no effect on the orbital speed. Wait, satellite has 1 or 2? I think it's just 1. Satellite. That doesn't look right. Satellite has no effect on orbital speed. If in the same orbit. And again, we see that is coming from the fact that we could just write our equation here and see that period equals square root 4 pi squared r cubed divided by gme. We see there's no mass of the satellite in this equation, so I could say mass of the satellite does not factor in this equation. Or we see that comes about when mass times centripetal acceleration as gravitational constant, mass of the satellite, mass of the Earth divided by radius of the orbit squared. Mass of the satellite disappears. All right, so let's see where they get points. So this was only worth 1 point. Correct answer. So yeah, so here is where things get a little bit messy. So the correct answer is equal to. So if you wrote equal to and you got your answer correct up here and you explain it, you get the point. But let's say you wrote something less than or greater than and you got this expression wrong. So if you got the expression wrong here and you had mass of the satellite in the equation, then you could do greater than or less than. And if you're consistent, you can still earn that point. So let's say I put mass of the satellite in the numerator and that's wrong. So if I put mass of the satellite in the numerator, if mass of the satellite goes up, period would go up. So I could say greater than if I messed this one up, and I would still get that point. So that's where you have to kind of think. Or if you put mass of the satellite in the denominator and you got that incorrect. So if mass of the satellite goes up, period goes down. So you could write less than as long as it's equivalent to your answer. But yeah, so here, if we got this right, correct explanation that the period of the spacecraft does not depend on the spacecraft mass, or that it only depends on the mass of the Earth and radius of the orbit, or an explanation consistent with the previous part if you messed up the previous part. But yeah, the explanation has to be consistent with the checked answer. So here's where if you had a correct explanation, but you wrote less than and you got this correct, you can't get the point. It's kind of a lot of if-then type things going on here. Anyone uncertain if they got the point? All right, I think that one's kind of straightforward. So now we change the radius. Now the first spacecraft, so that mass m, is moved to a new circular orbit with a radius greater than r, as shown in the figure below. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? Greater than, so faster, slower, or same speed? All right, that is the correct answer. See, the speed is going to be less than the initial speed. So we can get here, and this is where we can go through this a few ways. We do have our equations. We can go back to our mass times centripetal acceleration is gravitational constant, mass of the satellite, mass of the Earth divided by radius of the orbit squared. Mass of the satellite doesn't matter. Speed squared divided by radius of the orbit. Gravitational constant, mass of the Earth divided by radius of the orbit squared. Multiply radius over. So we see speed squared is gravitational constant, mass of the Earth divided by radius of the orbit. Now, I guess I'll take the square root. It doesn't really matter. Square root, gravitational constant, mass of the Earth divided by the radius of the orbit. So we see as orbital radius increases, the orbital speed decreases. Because radius is in the denominator. So that's one way. We could say with our equation, denominator, I think that's, yeah, denominator. So yeah, so we could say with our equation, we could derive this. We see radius is being divided by, so if radius goes up, speed goes down. Or we don't even necessarily have to go that far. We should be able to just say, as my radius increases, I have a smaller centripetal force. As I have a smaller, well, I have a smaller gravitational force, I have a smaller centripetal force. As I have a smaller centripetal force, I have a smaller speed. And let's see where their points are for this one. So only 1 point, correct answer. So you had to get the correct answer. You had to get less than in order to get the points. But here, if the wrong selection is made, the explanation is not graded. So this is kind of back to one of those things where if you have no idea what the answer is, don't guess. If you're pretty confident what the answer is, you should check one. But yeah, if you have no idea, don't guess, because here it says if the wrong selection is made, don't grade the answer. But it doesn't say you have to have the correct answer to get the point for the explanation. So sometimes you have to get the correct answer to get the point. So if you know the answer, if you know it's less than and you're confident, check that. If you have no idea, it's better to not check this. And then, yeah, so correct explanation, y speed decreases with increasing orbital radius. So you could just say from the derivation, you didn't even have to redo that. You could just say in step B1, we saw that bigger radius leads to a smaller speed, or something like that, or just pretty much anything along those lines. So that was the easier question and the shorter question. So hopefully that was all right. Again, a passing score that's going to be like 4 out of 7 or more. So hopefully you're getting 4 or more, or at least 3, kind of getting yourself close to the passing amount. All right. So let's look at this next one. Yeah, I like derivations and graphs too. Yeah, there is no lab question this year, so that's good for you. The lab questions are randomly not so bad though. You really just have to say, like, get an equation and then just say measure this with this, measure this with this, measure that with that, and then use this equation. And it really is kind of straightforward, but yeah, I can see why it's definitely a struggle. The struggle is figuring out the correct equation, honestly, with that. But yeah. Yeah, there is more writing. I definitely, one thing to watch out for this test is I really think there's more writing. Again, with how they're trying to encourage you to write out your responses on Google Classroom, or not Google Classroom, on a Word document and then post it on the actual AP test. I don't think there's going to be a lot of derivations, so you probably will still be writing a good amount. Life hack for computer testing. I think that's just a normal computer hack. But yeah, and the other thing, the week of the AP test, we're probably going to do. Does it really? That's actually pretty convenient. Um, I would watch out. One thing is I don't know how formatting is going to work. Sometimes their formatting gets off when you upload something. So you might be better served by just writing pi as pi and square root as sqrt. You can do that. And if they give you the actual practice AP test, which is supposed to happen Monday next week, and you try that, then hopefully you can see if it actually works. If not, then yeah, I would go through and just type out the values or mu for mu. But yeah, if you are able to test that and it works, then definitely that can be a really nice way of doing this. All right, so yeah, getting back to it, not next week, but the week after that, the week of the AP test, one of those days we're going to go through and I'm going to help you make a cheat sheet and connections with all of those. I'm not going to tell you exactly what to write, but we'll kind of work through that. I have 2 kind of things. One is just kind of mapping the different concepts and how they're connected, so a little bit more of an abstract thing, and then I want you to use that to try to make a cheat sheet of a few pages that are really organized to help you for the test. So, yeah, SQRT is probably what I would say to do, an MU for mu. Yeah, Wolfram Alpha, again, you go to formatting issues. I know for one of the things that happens is if you notice, if I upload on Google Classroom, if I upload a Word document with those special characters, the special characters just immediately disappear. And so I don't, that's going from Word to Google Docs, and it messes it up. Yeah, and so it kind of depends what their formatting is. So it might be better to just type out the symbols as opposed to trying to put the actual symbol in. We'll see. Hopefully next Monday we get a better idea about that. All right, so let's keep going so I don't do this too long. Yeah, you do have the choice to upload a picture. That the thing is, if you upload the picture, you need to take the test on your phone. That way you're looking at it on your phone and then you take a picture from your phone. Just don't be expecting to take the test on your computer, then take a picture and somehow get the picture to your computer to upload it. it can be interpreted by Wolfram alphas. Yeah, so that's what I'm saying. Yeah, so typing things out like SQRT or MU or PI, like actually typing the things out is probably going to be it would be probably less risky that your formatting gets destroyed whenever you turn in the test. Or if you type it, you might be able to export it to a PDF and turn a PDF in. That's how I upload the things is as PDFs, because then the formatting just is stuck that way. But yeah, so if you do the symbols and you make it into a PDF and then you upload the PDF, then you 100% will be able to see the symbols. As long as they don't have limits on the type of documents you can upload. All right, so looking at this one, we're on to everyone's favorite, rotational motion. I know everyone loves rotational motion. The disc shown above spins about the axle at its center. The student experiments reveal that while the disc is spinning, friction between the axle and disc exerts a constant torque on the disc. Yeah, I don't think this one is too terrible. It actually, you can use kinematics for a good amount of this, so hopefully not too bad. So at time t equals 0, the disk has an initial counterclockwise, and they gave you counterclockwise as positive. So again, remember our kind of things for this. Normally counterclockwise is positive and clockwise is negative. They'll probably tell you which one to use. Angular velocity omega naught. The disk comes to rest at time t equals t1. On the grid at the left below, sketch a graph that could represent the disk's angular velocity as a function of time t from times t equals 0 until the disk comes to rest at time t equals t1. All right, so first off, let's start by going through our endpoints. So time t, t1 is right here. What speed do we start at? Omega naught. Negative omega naught. So we start at a positive omega naught up here. And then what speed are we at time t1? We stop. Okay. And then there's a constant torque. Constant torque. Well, we know that angular acceleration is that net torque divided by moment of inertia. So I have a constant net torque. Moment of inertia isn't changing. I'm not changing the mass or radius of this thing. So I have a constant angular acceleration. So is this going to be a straight line or a curve? Yeah, straight line. So I have a constant acceleration. So I have a constant slope on my velocity time graph. So constant acceleration, which means I have a constant change in velocity with respect to time, right? Acceleration is change in velocity over time. And notice how I can use those words interchangeably. Constant angular acceleration, so constant change in angular velocity, or constant acceleration, constant change in velocity. And then we are slowing down to 0. All right, and then we have our angular acceleration here. Yeah, question that I was just about to say that too. Question part 2 is a little bit easier than part 1, even though it doesn't seem that way. The nice thing, because this is talking about our angular acceleration, so this is 0. Notice they don't give us a scale here. It's just kind of implied positive, negative angular acceleration. So do we have a positive or negative angular acceleration? Yeah, negative. We go from positive omega naught to 0 angular velocity. So that means we're moving in the negative direction. From positive to 0, moving in the negative direction. And then constant negative, increasing or decreasing negative. And it's not just slows to a stop, because I could easily have a situation where I go from negative omega naught to 0, and that would be a positive angular acceleration. So it's not that it slows to a stop that makes it negative. It's that it goes from positive to 0, or 0 to more negative. We're just moving in the negative direction. Our velocity moves towards the negative direction, so we have a negative acceleration. We have a constant negative acceleration. Again, if you're writing this on paper, let's make sure we actually label our time axis, otherwise I can't tell these two apart. But yeah, we have a constant negative angular acceleration because we have a constant torque. So constant torque is just like constant force. Constant force, I have a constant acceleration. Constant net torque, I have a constant angular acceleration. I go from positive to 0, so I'm moving in the negative direction for my angular velocity, so I have a negative constant acceleration. All right. So looking at this, so example graphs look pretty much like our picture. So for this one, you definitely have to go from positive omega naught down to 0. Here, it doesn't matter where we put our negative line. Notice we don't have a scale here. All we have is a 0. It just matters that we have a constant negative acceleration. So you could have drawn it a little bit lower, a little bit higher, so closer or further from the 0 and still be good. All right, so the first point is for a curve that has an angular velocity positive omega naught at time t equals 0 and decreases to 0, t equals t1. All that's saying is we start here and end here. It doesn't matter how we get here, as long as I start here and end here, we get that first point. Because a line is basically a curve that doesn't curve. So here, for a curve that is a straight line, I really like that statement. For a curve that's a straight line with a negative slope showing the angular velocity approaching 0. So here it doesn't have to start here. So it doesn't necessarily have to say it starts at omega naught. It just has to be a straight line with a negative slope that ends at 0. So it can be a positive slope if the initial angular velocity is negative. Oh, okay, so yeah, that's the other thing. If we put the initial down here at negative and put a positive here, you would get that 1 point. So let's say I put it down at a negative here and it goes up to 0. That gives us one of the 2 points. Or if I go from here to here, I get a point for it just starting here and ending here, and I get a point for it to being a straight line. All right, that was 2 points. And then we get 2 points for angular acceleration. It sounds like the questions is going to be 25 points for the 25-minute question and 15 points for the 15-minute question, because 5 of those minutes in the 30 and 20 minutes are just the upload time. So there's probably going to be a good amount of points per part like this, how you they're probably going to be throwing out points left and right for a lot of these things. And again, I really do think it's going to be a lot of different concepts, and it's probably not going to be building off each other for each part. At most, I think they might have like a part 1 and 2. So a few things is, I think it's probably going to be a type of thing where you can glance through the question and find different parts you might be able to solve C independently of any other part, or you might find E and you can do E independently of everything else. So I would look at that. The other thing is, it seems like they're trying to make this test like way longer than you could conceivably finish. So you might run out of time, and it sounds like they're trying to make it where no one will finish the test, and then that way it's hard to cheat. So another kind of guess based on what has been said. So your acceleration graph stay on the negative side the whole time, but the slope is not 0. Yeah, let's see. So for a curve that is negative the entire time, so if we're under the x-axis the entire time, yes, you get that point. I would say as long as it doesn't go to 0, I don't think you can hit the 0. So if you went from here to 0, I wouldn't give you the point. But if it stays below at all times, I would give you the point. Yeah, I think if you hit the 0, you lose that point based on what this says. because negative the entire time, 0 is not negative. That's just a guess. I don't know the exact way they scored that one, but I would say probably not. And then a curve, that's constant non-zero function. So constant, and notice it doesn't say constant negative. It just says constant non-zero. So if you had a constant positive slope, not constant positive, a constant positive 0 slope value, you got that second point. But it's just a horizontal line, you got a point, and then anything that just stays negative the entire time, you got the other point. I could be wrong. They may have given the point for that one. I'm not entirely certain. Yeah, they refer to the line as a curve. Yeah, I mean, so a, a line is a curve without a curve. But yeah, a lot of times they say the word curve just so that it's obvious. Oh, if you got anything, it doesn't matter as long as it was following that. Because if they say a line that stays 0, then that implies it has to be a straight line. Yeah, a line is just a curve with a 0-second derivative. If it's a continuous relation, we call it a curve. Yeah, I actually, the more I think about it, I don't know the exact mathematical definition for the word curve. All right, I like B because there's two ways of going through and doing this. So the magnitude of frictional torque exerted on the disk is tau naught. Derive an equation for the rotational inertia I of the disk in terms of tau naught, omega naught, and T1, and physical constants as appropriate. So the torque of the disk, so it's constant. We have the initial angular speed of the disk, and the final angular speed of the disk is 0. Well, velocity, because it's positive omega naught. And then time 1 is the time that we stop. All right. Moment of inertia. How can we do this? Well, we're given torque. Trying to find moment of inertia. That means probably going to use acceleration. Yeah, there we go. Angular acceleration is net torque divided by moment of inertia. And I think they should recognize exactly if you write it like that. I would write acceleration ACC because AC might look like centripetal acceleration. So angular acceleration is that net torque divided by moment of inertia. So I could divide divide moment of inertia over. Angular acceleration times moment of inertia is equal to net torque. Well, that's pretty close. We know that our torque is just tau naught. AC air conditioner. Yeah, that's the other thing it could be. But we don't know angular acceleration. How could I get angular acceleration? We can use kinematics. There we go. Rotational kinematics. For all of you that are obsessed with kinematics for whatever reason. Final angular velocity is equal to initial angular velocity plus angular acceleration times time. So our final angular velocity, we end at rest. This whole thing stops. We start with positive omega naught. Plus we don't know our angular acceleration, and our time is t1. We go from 0 seconds to t1 seconds before we stop. Subtract this over. So negative initial angular velocity, well, angular speed, the negative makes the velocity, is equal to angular acceleration times time 1, divide time 1 over. Angular acceleration is negative initial angular speed divided by time 1. Put this in over here. So negative initial angular speed divided by time 1 is equal to, my moment of inertia, times moment of inertia is equal to that torque, multiply time, divide angular speed. So moment of inertia is going to be equal to the initial torque times time 1 divided by the initial angular speed, we get a negative. Now, moment of inertia cannot be negative. What's saving this from being negative? Which value in here has a negative inside of it? Torque, yeah, exactly, torque. So torque is in the clockwise direction. So whenever I substitute a number in for torque, that torque would be a negative number, and we'd have a negative to get a positive. So that's one way of doing B. But kinematics is boring. Sorry, all of you in the kinematics gang. There's way more fun ways of doing this. Anyone else know the other way of going about this without having already looked at the key? It's the way I like way more, because it's the way, if you ever go through physics, it's the way you're actually going to do it. No one in physics ever uses kinematics after like the introduction of it. That's a lie. There is a little bit of kinematics, but we could also use change in angular momentum, right? Our angular impulse, our change in angular momentum is torque times time. Well, that looks pretty useful because torque is given to us, so torque times time. Well, change in angular momentum is final minus initial angular momentum is torque times time, T naught times time 1. Final angular momentum, well, that's just 0. Stop spinning minus moment of inertia times the initial angular speed, right? Angular momentum is moment of inertia times angular velocity. Angular velocity is positive omega naught. This is all equal to that initial torque times time 1. Then we can just divide the initial angular speed over. So moment of inertia is that torque times time 1 divided by initial angular speed. Put the negative on the other side, multiply both sides by -1. And that's even less work, which is why angular momentum is superior to kinematics. And we see we get either of these. So for this one, the equation for rotational version of Newton's second law, F equals ma. The rotational Newton's second law is torque equals moment of inertia times angular acceleration. So if you use that, and then using rotational kinematics, angular acceleration, change in angular velocity divided by time, that's the exact equation we use, just not solved. Final angular velocity equals initial angular velocity plus angular acceleration times time. And then we go through and then we derive this expression, which is what we got. And they say we still are in the point if there's a minus sign. Again, the minus sign comes in because we're not assuming the torque is going to be positive. So yeah, we got the negative. I would say that's technically more correct, but it is what it is. And then the alternate solution would be going through using angular momentum, torque, so rotational impulse is this, and then we drive this, and I say this is faster and better. But yeah, a lot of you are probably going to default to kinematics, and that's fine. Kinematics works just fine right here. And these are all types of things I could see them asking this level of math, because there's not a whole lot to write here. I could see them giving you this level of math and expecting you to type it out. And anytime you see like a delta, you can just type out delta omega. I would write if you write a delta, I would do something like delta and then omega. I would do some sort of parentheses, almost like delta is a function. It's just a little bit easier to read what is changing. All right. So we're on C. In another experiment, the disk again has an initial positive angular velocity omega naught at time t equals 0. At time t equals 1/2 t1, the student starts dripping oil on the contact surface between the axle and disk to reduce the friction. So at halfway through, our friction starts decreasing. So as time passes, more and more oil reaches the contact surface, reducing the friction even further. So our friction doesn't just decrease immediately, it decreases and keeps decreasing. So on the grid on the left below, sketch a graph that could represent the disk's angular velocity as a function of time from t equals 0 to t equals 1, t1, which is the time in which the disk comes to a rest in part A. Notice it says the time the disk comes to a rest in part A. So if we leave this going for the same amount of time, but our torque is decreasing because our friction is decreasing, are we going to come to a rest here in the same amount of time? Or is it going to spin longer or spin not as long? Yeah, it's going to spin longer, right? We put the oil on it, so there's less friction. This thing is going to spin for longer. So when we get to time t1, this thing is still going to be spinning. So let's go through, break this up again. So we have positive omega naught, 0, negative omega naught. We still started that positive omega naught. Now we have two important times going on. So we have times t1 over 2. Then we have that entire time t1. Let's be really careful to actually label our time. Probably not going to get a graph question. They could, yeah, I still don't see them asking you a sketch question, but it's still important to think about. I could see them asking you this question. Probably shouldn't even write that. I could see them asking you this question more as explain what happens as opposed to draw out what happens. Well, it looks like I'm doing time 1/2, but it's time 1 divided by 2. So let's write that a little bit better. All right, so before we start introducing friction from here to here, what's our graph going to look like? This little section here compared to here, it's going to be exactly the same, right? From 0 to t1 over 2, we're not adding any oil. So originally we did this, right? So I could go there and then let's erase this. But this section here, we haven't started adding oil yet. I start adding oil when I get to time t1 over 2. So this section here is going to look exactly the same. Now, as I add oil, this final speed, is it still going to go to 0 at the same time? The oil reduces friction, so it's going to keep spinning for longer. So by the time I get to the same time as I did up here, it's still going to be spinning, right? So it's still going to be spinning. It's still going to be moving here. If I have less friction and it's been going for the same amount of time, it's still going to be spinning there. Now we have to get to how we connect this last little bit here. Is this a straight line? Does my acceleration suddenly change to a new smaller acceleration? We see our torque decreases over time, which means the angular acceleration decreases over time. And that means that our slope of angular velocity versus time goes down over time. So it doesn't suddenly decrease the slope. Our slope is decreasing over time, which is implying kind of a curve. Which is, yeah, maybe I need to draw this a little bit lower. It's going to curve and not make its way to 0. We start with a bigger slope, but as I get more and more oil, the slope gets less and less as this accelerates at a slower and slower rate. A curved, yes, a curved curve as opposed to a linear curve. Oh man. But not a curved curve. All right, so we have here again. I don't know why that made me laugh so much. We have here again from time t equals 0 to half the way there, we have the exact same situation here where we have a constant negative acceleration. But then we get to this point here. Wait, a straight curved? Is it a straight curved curve or a curved straight curve? So our acceleration decreases over time, but again, the magnitude of acceleration decreases over time, right? These are vectors. So that means my angular acceleration gets less negative over time. And then it just says reducing friction even further. So it doesn't explicitly state how this goes, but it should be angular acceleration is getting less negative over time. It doesn't say friction is completely reduced, so I didn't draw that all the way to the 0. I forget how they actually score this, whether they say it can't go to 0 or not. I would say it shouldn't go to 0 because you're adding oil, but it doesn't say friction goes completely away. It just says reducing friction even further, not reducing friction to 0. If friction went to 0, then our angular acceleration would go to 0. But it kind of implies that our friction doesn't go completely to 0. So I would say it implies that angular acceleration doesn't go to 0. Test curve is the best curve. Well, your test curve is actually a line. Every time I do your test curve, I take a line and I transform the line by changing the slope and the y-intercept. So your test curve is a linear curve as opposed to a bell curve. All right, so this is 4 points. So yeah, quite a bit of points to be earned here. So 3 points. So a curve with a clear change of slope or curvature at 1/2 t and showing a decrease in speed thereafter. So yeah, that's talking about this point. So from here to here, you get a point. The slope has to start curving, and you have to still have a decreasing speed. Now, yeah, based on how they said that, I would argue that if you somehow did a stupid curve like this, like concave down instead of up, I think that still gets the point. I hope no one did that because that wouldn't make sense to have a sharp turn. But yeah, the slope is getting less negative as we get there. You did it. Sorry, I didn't mean to imply anything. But yeah, I think if you did it the other way, I think you still get that point based on the wording here. So yeah, you do get that point. Yeah, you 100% get that point because this is what the next one is saying. For a curve that indicates a slowing at a decreasing rate. So it slows at a decreasing rate. So in other words, we go from steep to less steep. So that's the second point. You go from steep to less steep. So if you went the other way, concave down, you don't get the second one. Oh yeah, you can't touch 0, no. Well, so you don't get the third one, but you still get this one. Because it doesn't say it doesn't hit 0 here. So if you did a curve like this down to 0, you get 1 point. Because you still earn this one. So yeah, so 1 point, it goes, you have a change in slope, and the speed is still going down. So we're still getting lower on our y-axis. The curve, it slows down with the decreasing rate. So pretty much concave up, steep to less steep. And then the curve does not reach 0 at or before time t equals 0. If you drew it out and it went down to 0 down here, you can still get that point. It just can't hit 0 at time t1 or before that. Because again, that goes back to the previous one where this one has lots of friction and it stops at time t1. So if we take away friction, it has to take a longer amount of time to stop. So it has to stop somewhere past time 1. And that's why you can't hit 0 there. So most of the points were for this graph. And then only 1 point for this graph. So 2, a curve with decreasing magnitudes between times 1/2 t1 and t1. So it says the acceleration may reach 0 at or before time 1, but if it reaches 0, it has to remain 0. So yeah, what they're getting at is that it goes here, and then we have a decreasing acceleration up to here. It doesn't care if it's a straight line or curved. They didn't give us enough information to say whether it should be curved or straight. But they do say if you get to 0, it has to stay 0. You can't go to 0 and then go to positive acceleration. That would be wrong, saying you're suddenly accelerating in the opposite direction. Adding the oil isn't going to start turning it the other way, so I can't put it up this way. All right, so it doesn't have to stop below this. It can go to the 0, but it can't go past the 0. It doesn't have to be a straight line. It could be a straight line. It could be a curve, but it just has to be getting less negative. And actually, what does this actually say? Curve with decreasing magnitude. Actually, decreasing magnitude, so it doesn't even have to be that. If you drew a positive acceleration here and it's going towards 0, you get that point also. So if any of you drew a positive line here and then it's going down towards 0 in a line or a curve, you get that point because the magnitude is decreasing. You're going towards 0. So another random place you can get a point. All right, last little bit. The student is trying to mathematically model the magnitude of torque exerted on the axle by the axle on the disc when the oil is present between times, past 1/2 t1. The student writes down the following 2 equations, each of which includes a positive constant c1 or c2. Positive constant, that's important. The constant can't be negative with appropriate units. So we can't use this constant to flip around a positive or a negative for us. And it's just a constant, so we can almost just kind of think of that as a 1. I'll still write them here. This is D. We have our 2 equations, so equation 1. This is exactly the type of question I expect them to ask here, because it's going to be a really wordy response saying why the equation works or not. So I almost expect them more, instead of asking you to derive something, I expect them to ask you to say, does this derivation make sense? And because all of them will be like that, I'm guessing that a good amount of the derivations they say will make sense. I mean, these are all just completely guesses by me, but I would say you're probably going to be looking at their derivations as opposed to making the derivations yourself. Time is greater than 1/2 t1, which means you might need to make the derivation off to the side. If it's something they're asking, is this a correct derivation or what did you do wrong? You might have to do something to the side to figure it out. This one, torque is equal to constant 2 divided by t plus 1/2 times 1. So which equation better mathematically models the experiment? So let's look. Which one of these doesn't? Which one of these fails pretty miserably? And one thing to notice, time 1 is a constant, right? Time 1 is a constant number. Time 1 could be, say, 1 second. So let's actually go through and do those. Let's change these out for numbers. If it's a constant, I'm just going to put a 1. So let's say for equation 1, this would be torque is equal to 1. I mean, that's not a perfect. Obviously, it could be something different than this. 1 times t is my actual variable minus 1/2. Time 1 again is just a number. That's the final time when this thing stopped initially. So that's not a variable. I can leave this at 1. So this is going to be probably shouldn't write equal to. It's going to be pretty much just t minus 1/2. This would be pretty much just 1 divided by, again, t without a subscript is our actual variable here, plus 1/2 time 1, that's just a number. That was the initial time that the wheel stopped spinning. So that's not a variable. That's just a number of seconds that we definitively know. T is our actual variable. Does that make sense why t is the actual variable? T1 is not your variable. T is, yeah, that's the other way. Look at your actual graph. That's another good way. So T1 is a specific time on your graph, but T is the actual variable on our graph. All right. So looking at these, so which one of these fails miserably? What's happening to our torque over time? Is the torque going up or down over time? So again, before we answer this, let's talk about our explanation first. Right? There's no reason we have to answer the question before explaining. So after, probably capitalize that, after time t equals 1/2 t1, what's happening to my torque? Does torque go up or down? Torque decreases as oil is added. So oil is added, we get less and less friction, so we have less and less torque. So torque by friction, by that force of friction, decreases, right? Because friction is what's causing the torque. So I expect torque to decrease as time goes up. So let's look at this one. So as time goes up, does torque go up or down? So as time increases, comma, torque increases. Right? Because this is in the numerator. As this number gets bigger, I have a number minus a constant. Time goes up, this number minus this constant. This keeps getting bigger. This is a constant. So a bigger number times a constant is going to be a bigger torque. So this is in the numerator. As this gets bigger, then torque increases. So in the equation 1, as time increases, torque increases, which does not match the experiment. Which does not match the, should I say this? Does not match the prediction. All right, so let's look at equation 2. And equation 2, all right, this is in my denominator. As time increases, what happens? Torque decreases, torque goes down. This is in my denominator. I have a time goes up, so the number plus 1 goes up. I'm dividing by a bigger number, so my torque goes down. In equation 2, as time increases, torque decreases, which matches my prediction. So which one is correct? Or more correct? So equation 2 is more correct. And this is one of those ones that didn't seem like any of you immediately knew which equation to use. So don't immediately guess equation 1 or 2. Start writing here, and by the time you've written, if you get to a point where you're sure of an answer, then you can check the answer. But if you've still written a few things and you're still uncertain, just don't select an answer. Change in angular momentum equals torque times time. Um, yeah, I mean that's the yeah, you could use that. And so you could use talking about how you're having a smaller change in angular momentum. So as your I mean, I guess, yeah. So you would say for a constant, yeah, that would be what it would be. So for a constant change in angular momentum going from positive omega naught to zero, um, my angular acceleration decreases. Well, my change is staying the same, but my torque decreases, so I expect a longer time. You could do something like that. So that's another way of showing that as your torque goes down, your time to stop goes up, or your time to change the angular momentum goes up. Yeah, you can talk about it that way also. You're not going to derive the equation from this though. Yeah, it's you could, but the constant thing is going to really mess with you if you're trying to derive this. I mean, maybe some of you could do that, but I would say you don't need to do that. So this was only worth 1 point. So if you made the wrong selection, the explanation is not graded. So this is where I'm talking about it's good to go through and start doing your explanation first. And then if you figure out the correct answer, then definitely select it. But if you're going through your explanation and you're uncertain what the answer is, just don't select something. If you're still uncertain, notice you didn't, if you don't select something, you did not make the wrong selection. So if you're not sure, don't select anything, and then they can still grade your explanation, which is kind of weird to me, but it's how they grade. So here we have to state that equation 2 is plausible because the frictional torque decreases with increasing time, but equation 1, the torque increases with increasing time. That's pretty much what I said. All right. Any questions on these? We're getting pretty close to the more recent AP tests, so this is the 2018 one, and then we'll go through the 2019 one. And we're actually going to run out of them, and so we'll have to do some that probably some NIMSY ones that they've made. But yeah, no other questions. This went on a little bit longer than the other ones. Again, a few things to look at. Make sure you watch the College Board video. It contains really good information. It shows what your test is going to look like and the steps you're going to go through and how it's going to work. Hopefully, they'll put out the practice test so you can actually go through and check things on Monday. And I'll be looking for that and try to help you go through it. Again, just keep working on these. If you haven't done the mock test or the simple harmonic motion test, do those, get those in, catch up on your homework if you're behind. And yeah, just a little bit longer to go. So just 2 weeks, really work, get your things in, catch up, and then you're done with AP Physics unless you go on to one of the other ones. So other than that, good luck on these and have a good day.